Okay. Position at S lambda of X is some X the weight of T as T runs over semistandard Young tableaux of shape lambda. Okay. Proof. So there are different proofs of that. Actually, like the material that is of today's lecture, you can find in the book Young Tableaux, I think, Young Tableaux by Fulton Harris. And the proof that I'm giving to you is rather elementary, and you can understand everything. And in particular, it's given in the following note. So C Proctor. So Proctor is the name. Proctor, like an article, a note called equivalence of the combinatorial and the classical definitions of Schur functions. So we'll first start with the following lemma. So how to express, lemma S lambda of x1, xn, how to express Schur function of n variables in terms of Schur functions of n-1 variables, first n-1. The sum S mu of x1, xn minus 1, xn to the power lambda minus mu. So recall that this was the notation for the sum of all lambda i's. So it's sum of all lambda i's minus sum of all the mu i's. Okay, proof of lemma. So we just, for simplicity, we just take some special case, and you see that everything can be like in general. You can do the same stuff, right? So the pattern is clear from just this special case. So for lambda equals 4 to 1, and respectively n equals 3, right? In this case. So lambda 1 is 4, lambda 2 is 2, lambda 3 is 1. In this case, determinant of xj lambda, so lambda I plus n minus I, the numerator in the Weil's denominator in the Weil's character formula, it's what is determinant of such matrix. So we have x to the power 4 plus 2, and x1, x2, x3 will be labeled a little bit differently. Since there are three of them, we can take x, y, z. Okay. So x, y, 4 plus 2, z, 4 plus 2. And then x, 2 plus 1, y, 2 plus 1, z, 2 plus 1. And then x, 1 plus 0, y, 1 plus 0, z, 1 plus 0. You see the pattern, right? So what's here, 1 to 4, 1 to 4 is this lambda. And then plus n minus I is this 0, 1, 2, 0, 1, 2, 0, 1, 2 is this part. And yes, this is how we change from row to row, and from column to column we just change variable. Okay. So how do you do? So what is the next step? We take z equals to 1. Remember z is xn in this case, right? And we subtract last column from the rest of the columns. So last column is x, y, z. You subtract from this and then divide. Okay, so then what happens? Then I will have x. Right. Yes, last column. Right. Last column is 1. Right. So I will have. It's just 1, 1, 1 will be if I take z equals to 1. Right, and subtract from this one, I will have x to some power minus 1. X to some power minus 1 I can factor out x minus 1, and the rest will be, it's known what it is, right? So I will have x minus 1 in the first column, so I can factor it out. And similarly from the second one, we'll have y minus 1. And then what's left? So actually, the general formula, I believe, so x to the L minus 1 is x minus 1 to x to L minus 1 plus x to minus 2, and so on. Right? So we use it here, and I will have here x to the 5 plus x to the 4 plus and so on. Plus 1. Here I will have x squared plus x2 plus 1. In here 1. So determinant of this, of course. Here I will have y to the power 5. Yes, x squared plus x plus 1. Mm-hmm. The same with y. Y squared plus y plus 1, 1. And then 1, 1, 1. This equals to, again, x minus 1, y minus 1, determinant. And I would like to subtract, so I take like this, take first column, subtract second. Take second, subtract third. Yeah, so I start, so from this y, so from this one, I'm subtracting the previous one. So what will be left is x5 plus x4 plus x cubed. And then x squared plus x plus 1 will be subtracted. Okay, so x to the 5 plus x to the 4 plus x to the 3. Actually, I never finished the formulation of propositions. But first let me finish this. Determinant of this, x square plus x, 1. And then I have y to the power 5, 4, 3, square plus y, 1, 1, 0, 0. Yeah, okay. What are we proving? So here, what is mu? It's important. So mu here. So sum over all mu such that, so mu has its own entries, mu n minus 1. And I have, so this mu i's, they sit in between lambda i's. So I have lambda 1, then I have mu 1, then I have lambda 2, then I have mu 2, and so on. And then I have mu n minus 1, lambda n. Over all mu such that I can put them like mu I between lambda I minus 1, lambda I plus 1. Okay? Okay. So, but look at this determinant. Right. Okay. So we have sorry. We already rewrite it here. So actually, what I have x minus 1 times y minus 1 times determinant 2 by 2 now. Right. Y to the 5th plus y to the 4th plus y cubed. All right. So actually, similarly, we can write like just doing the same type of operations, elementary row and column operations. That's the only thing that we are doing. We can rewrite the Weyl denominator, the denominator in S lambda. So we have determinant of x, j, n minus I. In this particular case, it will be x minus 1 times y minus 1 times the determinant of x, y, 1, 1. Okay. So, but then okay, so let me now take S lambda x, y, I put z equals to 1, right? So 1. And then this is actually, so this is determinant of x, j to lambda I plus n minus I, right, over determinant of x, j plus xj to the n minus I. So these two we rewrote like this, right? So let me denote this determinant as d1 and this one as d2, right? So I divide this by this, this by this, x minus 1 times y minus 1 cancels, right? It is in numerator and in denominator, so it cancels, right? So what happens is just d1 over d2. Nothing is said now, but what I claim is that this is actually s sum over mu, s mu of xy, where sum is the same as there over all mu's that I interlaced with lambdas like that. So why it's like that? You just need to see at what terms we have here, right? So all these s mu's, they will be of the form x to some power, y to some power, x to some power, y to some power, right? And what power can be erased, can be in here. So okay, we need to check. We need to see that mu1, it's related to mu1, right? Right. So here, right. So mu1 is between lambda 1 and lambda 2.
Excuse me, Professor?
Yes.
Sorry, I think I got lost. What is this S lambda xy1?
Say it again.
I
Say.
don't understand a bit of notation. I understand up to the last third line, the determinant of this xj and minus 1 and minus I is equal to this. I understand this. But then you wrote something like S lambda xy1.
Yes. So my s lambda is now a function of three variables, x, y, and z. We agreed in the beginning that I'm posing z equals to 1. So that's what I mean. So this is s lambda of x, y, z, where I put the z equals to 1. So this it's again relation of two determinants where I put z equals to 1, right? And x1, x2, x3 is x, y, z, right? It's d1 over d2, because I can now cancel this common factor. But then I claim that d1 over d2 is exactly the sum that we need, but only without z. But so we're not looking at z at the moment. So I am claiming that you just choose from each entry here any term from each entry. And this will give me S mu for some mu that satisfies this property. For example, look at this entry. It's x5 to the x4 and x3. And the condition that, so this entry is what? It's x to the power 1 plus mu, right? 1 plus mu1. Because, well, you just need to check, again, S mu is determinant of x to the mu I plus n minus I over determinant of something, right? So again, the lower determinant is exactly what we obtained here. And the upper, well, so the summation is over all these choices. Term in here, term in here, term in here, and term in here. So let me see that all terms in here are exactly that are in the matrix in numerator of S mu, right? So entry in here in the numerator of S mu is given by mu1, and it's actually should be like this. So mu1 is between lambda 1 and lambda 2, so it's actually what? Lambda 1 is 4 and lambda 2 is 2. So it's mu1 can be 4, 3, or 2. Right? The only possibilities. So therefore, in this corner, x can be either in fifth power, or in fourth, or in third. That's exactly what we got here. And you can check that this is also exactly given in all powers that we can obtain in this sum. And the same is here. But now you should check mu2, which is between lambda 2 and lambda 3. All possibilities are given by these two terms. And that's it. So it's a pretty elementary stuff. You just need to trace over all that. This particular example gives you like the sense of how it's done. But in general, it's just the same. The same procedure. It's just harder to explain.
Okay, so just that we did this for a particular case of lambda where we assumed that there is n equals to 3 and lambda is equal to 1.
Yes. We didn't finish. We didn't finish. We proved only for where z equals to 1. But then we need to prove this. But this is done by actually noticing that S lambda, so S lambda is actually a homogeneous polynomial of degree the number of boxes in lambda. So you can check it again. It's just you just look at the formula and you see it. It's harder to explain just to see it. So S lambda is homogeneous of degree lambda. So homogeneous means that you take any, so you have monomials there, and you sum up over all exponentials that appear in these monomials. And you'll get some number. And this number is the same for all monomials, and it's like that. So that's what it means, that it's homogeneous of this degree. So therefore, we know how much we should add. So this has total degree mu, right? We should add some degree of z. Which degree? Just to make it total lambda. So it's lambda minus mu. Right? So therefore, we finish the proof just by saying that S lambda of x, y, z, here SS mu, x, y, and z we should add to get the degree that we have in here, lambda minus mu. And that's exactly what it is here. All right. So next step is how to obtain the formula for S lambda using this. Okay. So we actually take and apply this lemma like a lot of times, like n minus 1 times, right? So then apply it to S mu. It will be S mu of x in this case, but actually like two less variables, and then 3 less variables, and so on. So what do we get? So apply. Was it lemma or what? Lemma. Yes. Okay. Apply lemma. How much? N minus 1 times to S lambda.
Did we prove this lemma?
Yes, we did. So we proved without z.
Yes, for x, y, z is 3.
Yeah. So I illustrated the proof for this particular case, but the claim is that it's just the same. If you think you just can do these procedures for any, I just picked this one just to show you how it works. Just not to write like a huge formulas on the board, okay? But the claim is that it works exactly the same in general case. Okay, so what is then? You have S lambda of x1 to xn equals to sum over something that I will need to specify. But what's on the top I also need to specify. Okay, so first of all, over which set this sum is. So it's over sets of partitions. I should say, well, this partitions or Young diagrams, if you wish. So let me denote it like this: lambda z. Okay, lambda 1, lambda 2, lambda n minus 1. This runs over what's called Gelfand-Zeitlin patterns of lambda. So what is this? So this is a Gelfand-Zeitlin patterns for lambda. So these are the following things. So first you pick lambda. It has this parts, lambda 1, lambda 2, and so on, and ends with lambda n. Right? Then you take lambda. So lambda 1 is another. So partition is a. I say sometimes I say this word partition. So partition is a bunch of integers, actually non-negative integers, such that they are non-decreasing. So like this. So lambda 1 is another partition, but the parts sits in between the parts of lambda. So lambda 1 is like that. So you have lambda 1, lambda 1, 1, and the last one is lambda n minus 1. So you have 2 here, and the last one is n minus 1. So for lambda 1, it's greater or equal than this one, but less, less or equal than this one, but greater or equal than this one. So you continue. So it's like that. So lambda labeled y1, its part sits in between this one. But then I just continue. So lambda 2 is here. I continue until I end up with just one number, which is lambda, I don't know, n minus 1, I think. So this one as well, it's like that. Yeah, so one data of numbers like that is called Gelfand-Zeitlin. It's the Gelfand-Zeitlin pattern corresponding to lambda. Lambda is the first row. And then you consider all combinations like this. So this one sits in between the previous row, this sits in between the previous row, and so on. All possible combinations of such things. So this is the set of all Gelfand-Zeitlin patterns corresponding to lambda. So this is the sum, and so this is another combinatorially very important in object mathematics. It appears in not only in here. So that's why it has this name. So and then you have x1 to lambda n minus 1 minus lambda n minus 2, x2 to the lambda n minus 2 minus lambda n minus 3, and so on. So if you apply the lemma n minus 1 2 times, you will get this. In particular, this means that okay, so maybe let me talk about all this has representation theoretical meaning. For example, this one, if you put 1, xn equals to 1, as we did in the proof, this will give you this what's called branching rules, how representation v lambda decomposes of gln decomposes representation of gln minus 1. Okay, so all right, but how to finish now our proposition? So we'll need some bijection between Gelfand-Zeitlin patterns. Yes.
Can you please explain this expression again? With x lambda of xn to xn is written as a sum over all these.
This one? Yes.
Yes, please.
Yes. So it's a sum. So the first row is fixed. Then you consider all positive integers that you can fill in here according to this rule, and sum of all such things. But then x1, then sum of which terms? Of monomials like that. And say x1 has which exponential. So you take sum, so these are all partitions, right? So this is just sum of all parts. So lambda n minus 1 is just lambda 1 n minus 1. Lambda n minus 2 module here is sum over the second from the bottom row. All right. So lambda n minus 3, you take n minus third row and sum over all elements of n minus third row, and so on. Mm-hmm. All right. So we need a bijection. If you take some pattern, Gelfand-Zeitlin pattern of shape lambda, you need to construct a corresponding semistandard Young tableau of shape lambda. How to do that? So you have a bunch of diagrams. You have a diagram for this one, and for this one, and so on, right? And actually, diagram, say for lambda 1, is inside of diagram of lambda. This is inside of diagram of lambda, and so on. Okay, so I can consider actually a set theoretic minus, right? So I take lambda I as a Young diagram, and remove all boxes corresponding to lambda I plus 1. This will be some number of boxes that didn't fit in here. All right. Okay. So I plus 1 or I minus 1, I think I plus 1, right? Because this one is smaller. Yes. Okay, very well. So the rule is the following. The boxes, and all these are boxes of the initial lambda, right? Because like they all fit in lambda actually, right? So there's lambda inside lambda 1 and then inside lambda 2 and so on, right? So to the boxes of this, put the number n minus I. Right, for I equals to starting from 0. Right, lambda 0 is lambda. Okay, so first you take lambda and then lambda 1. So everything from what is in lambda but not in lambda 1, you put n's in there. Then everything that is in lambda 1 but not in lambda 2, you put n minus 1 in there. And in this way, you construct T. Mm-hmm. So first of all, first question that you have to ask is why it's semistandard, right? It is semistandard because you have in each triangle, in each like local part of Gelfand-Zeitlin series, you have what? Okay, you have lambda j, right? I, and then you have lambda j plus 1, lambda j plus 1, I, this is greater or equal, and then you have lambda j and I plus 1. So we have like a local triangles like this. So this one is like that. So this ensures that there is no box on the top of box in lambda I minus lambda I plus 1. Why? Because this locally is the following picture. So you have, so this is, say, lambda I, and this is, so this is, locally it's like that. So this is lambda I j, this is row lambda ij, this is lambda I j plus 1. So this maybe I should do it like that. So so just consider two rows. This is row of lambda I plus 1, sorry, lambda j plus 1 I. This is lambda ji, and this is what's inside is lambda I plus 1 j. So this thing. So locally, inclusion is given like this. So that's what I mean. So you see, lambda j plus 1 is between this one and this one. That's exactly the condition in Gelfand-Zeitlin patterns. But this means that boxes from here never can be on the top of boxes in here. And the same is for any, if you go deep, like downstairs, you also have this. You have boxes in here on the top of boxes in here. So this is actually, but you put the same number in here and then in here. And this actually says that you never get a column with the same entry in this column when you do such a procedure. Okay, this is because of these local conditions. And because you go like step by step, it also increases. It increases by rows and columns. This is kind of clear, but why this strictly increases in columns? Because of these conditions, because of what I illustrated.
How many, for example, you have this map, given and P, you have how many blocks in a row, in the first row?
I don't know, lambda 1.
Number 1 box
Yes, in the first row. In the second, lambda 2 is just, like this. But then why it's bijection? Because you can present and some algorithm to go back. So you have everything that is filled with numbers from 1 to n minus 1 is lambda 1, right? You just throw away everything that is with n. Then you throw away everything with n minus 1. This will be the second row, and so on. So you can go backwards as well. So this is all very important because now the representations of GLN, they are combinatorially just they are labeled by semistandard Young tableaux. Well, if we finish proving it. But since we have a bijection, they are labeled by Gelfand-Zeitlin patterns. And you can just construct representation combinatorially. You just take, say, Gelfand-Zeitlin pattern and just explain in combinatorial ways how an element in X changes it, right? And this is a way how to construct, representations just labeled by such objects. Yes. So I think we proved everything, did we? Yes, almost. So I constructed a bijection, but also in my construction, this number is a number of ones. It's exactly the boxes that are in n-1, but not in n-2. These are where I put ones. So it's lambda 1 to the number of ones in my T. x2 to the power of 2's in T. So it's exactly, this one is exactly x to the weight of T, to which corresponds the such Gelfand-Zeitlin pattern. Yes. So I think we proved everything. So it's bijection and corresponding term corresponds to x to the weight T. So we proved the proposition. And moreover, we constructed some non-trivial bijection. And on the way, we also got some representation theoretic results. So for example, this lemma, it says so remark lemma previous lemma implies the following. It implies that what's called branching rule so if you consider V lambda the representation of GLN, then it's a direct sum of V mu's as a representation of GLN minus 1, where mu here is such that, well, we have this interlacing property. So what does it mean? It means that, okay, GLN minus 1 sits inside GLN. How you just take GLN is just all matrices, and you take upper left corner, and here sits GLN minus 1. So if you take a representation V lambda and restrict it to representation of GLN minus 1, It now it's not irreducible, but it decomposes into irreducibles. How it decomposes? Like that. Because we know this formula. It's just formula for characters. How this is a character of this representation, and this is the same character but decomposed into characters of irreducibles. So, you have to take xn equals to 1, right? Because I mean, since you consider gln minus 1, you don't consider enn. You just forget about this, and so it means that you put xn to be 1 in this setting. Yes. And also your vectors in your representations are labeled naturally by Gelfand-Zeitlin patterns. So you just take your vector. It sits first of all. It sits in some irreducible representation of gln minus 1, right? But then inside it sits also in some copy of representation of gln minus 2 and so on. And then you will be specified if you go to the bottom. And so this labels your each weight vector. Like it gives you a good basis in your representation of highest weight lambda for gln. Okay, so I'm finished. I think this is very fun combinatorics and pretty non-trivial. So if you look, so people are writing books, and different books you can find that.